Welcome back. This is the second part of our lecture on section 11.1. So in 11.1, we defined what a sequence was, an infinite sequence, and we learned that these sequences might converge, they might diverge, and our big problem from section 11.1, there's some other material in there in the first part of the video, but really the main part of this section is determining whether a given sequence converges or diverges. Okay, so I wanted to show some quick techniques. This section, there's going to be a lot of theorems, which might seem kind of clunky and abstract to you guys, but they are very powerful and they give us some very powerful tools. And then I'm going to show you just some little techniques as well. So this is something I would classify more as like a little technique, right? Not something we need to give a name to. Okay. And really, it's more about applying stuff from the first video. In the first video, I showed you this kind of L'Hopital's rule, but I also showed you the limit laws, right? So this is going to be one that kind of uses our limit laws a little bit. Okay. So let's say we were given this sequence here. Okay. And I want to figure out the limit of that sequence. Okay. So I need to figure out, all right, what's the limit of n squared plus 1 over n cubed plus 4? Does the limit even exist? Does the series converge? Okay. So I'm trying to determine if this has a limit. All right. Well, this is kind of complicated, right? I got a kind of complicated numerator, complicated denominator. All right. How can I make this simpler? Well, remember our limit laws that say, okay, if I can split this up under certain conditions, right? So this limit, first of all, I can split stuff up inside the limit without any problem. Does this help me? Well, I'd like to be able to split it up into two different limits. Okay, I'd like to split it up like this. Can I though? Well, if this is convergent and this is convergent, then that's fine. Okay, so let's look at this. So we don't know that this is equal, right? Let's look at these individual pieces. Does this piece converge? Okay. And here's, I'll kind of give you another technique to use. All right, if I have n, it kind of looks like infinity over infinity, right? As n goes to infinity, this top's going to get big, this bottom's going to get big. But with these polynomials and kind of simple functions of n, we can do a lot of factoring. So how can I factor this or do some cancellations to make this a bit cleaner? I'm going to factor out the smallest power of n, okay? I'm going to factor that out of the top and the bottom. All right, so what's the smallest power of n in this thing? N squared, right? N squared is smaller than n cubed. So let's try and factor that out. Okay, let's factor the n squared out of the top. Okay, if I did that, I'd have n squared times 1. And then let's factor it out of the bottom as well. And when I factor out of the bottom, I'd be left with n plus 4 over n squared, right? Okay, these two things are the same. And then this n squared over n squared, well, that's just 1. Okay. And now I'm left with this. Okay, what's this limit? What's the limit of this guy? Well, the top is constant, it's just 1. And then my bottom, what's going on with my bottom? Well, the n's getting really big, and then this is going to 0. But altogether, this denominator is going towards infinity, right? So I have a denominator that's going towards infinity. So 1 over that denominator, that should give me 0. Okay. So this limit equals 0, the limit of this left piece. Boom. 0. What about the limit of this thing? Well, there's just some simplification, some quick simplification I can do. 1 over n divided by n cubed plus 4, that's the same as 1 over n times n cubed plus 4, right? Which is equal to 1 over n to the fourth plus 4n. And what's going on with this thing as n goes to infinity? Well, that denominator is going to infinity as well. So the overall fraction should be going to 0. So that should go to 0. Okay. So these pieces, these individual pieces are convergent. They both converge to 0. So their sum, this thing, is going to be convergent, and it's going to converge to the sum of the limits. Okay, 0 plus 0 is 0. So the limit of this thing is 0. Okay. So a little technique to use, and that we really relied on those limit laws, right? Being able to split this this limit up into two pieces here, right? And then we just did some simplification. So that is going to be a lot of what you guys do in 11.1. These, the more basic limits you see are going to be things like that, and then we'll use some more advanced techniques. But this technique, this idea, is going to be very useful for the rest of chapter 11. So try this, try the exercises, and go back and look at the previous chapters on limits if you need to. Refresh your memory on limits. All right. Now let's talk about our first kind of big theorem from chapter or section 11.1. It's called the squeeze theorem. All right. So this is very useful. Let's say we have three sequences. We have a sequence AN, a sequence BN, sequence CN. And for every n, okay, here we've said for n greater than n naught. Okay, really this just means after eventually. We could think of this as saying eventually. Okay, so if eventually we have this inequality, if eventually AN is always less than or equal to BN, and BN is always less than or equal to CN, and AN and CN both have the same limit, L, well then that forces the limit of BN to be L as well. And the book has a nice little graphic. Let's say my AN are the blue dots, right? And AN is doing this. And we'll say L is kind of this line here, this value. Okay. So AN's getting closer and closer to L. And on the other hand, I have CN, which is getting closer and closer to L, right? Maybe from the other direction. And then I have this third sequence BN that's trapped in between my AN and my CN. Okay. So BN is doing something like this. Maybe it's bouncing back and forth between these two, but it's always trapped in between these two. So if the blue sequence and the green sequence are going to this line L, and my yellow sequence is trapped in between, then my yellow sequence has no choice but to go to L, right? It's got to have the limit L. Okay, so that's what this squeeze theorem is saying. So a quick example, when would you use, it seems like maybe this would be hard to apply, but think about this sequence here, sine of n over n. At first glance, this might be, again, kind of complicated. We know n is going to infinity, right? But what about what's going on when we factor in the denominator? Well, think about this. What do we know about sine? Sine, it doesn't matter what's in here, right? We could go ahead and put sine of n in there. It doesn't matter what n is, the sine of n is always between -1 and 1, right? And so sine of n over n is always between 1 over n and -1 over n. Okay. So I could think of this as like my AN, this is my BN, and this is my CN from the squeeze theorem. Okay. Now, what do I know about the limits of these things? Okay. The limit of this, think about the limit of this. Forget everything else, think about the limit of this. What is this limit? That limit's equal to 0, right? And what about this? Well, again, that limit is equal to 0. And this, my sequence, is always trapped in between these two, right? So the limit of this thing has to be 0. This has to go to 0. So maybe like that, it seems, I don't know, kind of obvious or something. Maybe it's not something you would come up with on your own, but maybe once you see it, you say, hey, that's really clear. Okay, so this is a common technique with the trig stuff. Okay, if you see the trig stuff and sequences, and later when we start talking about series, keep in mind this idea that sine is bounded, the trig stuff is bounded. Well, sine and cosine are, right? So sine and cosine are bounded. So if you ever get stuck on some trig stuff, maybe then squeeze there. Okay. Now, this is theorem 4 in the book. I've abbreviated the word theorem here as THM. Okay, so that just stands for theorem. Let's say the limit, well, the theorem is a bit different in the book. I'll kind of state it my way, which is a bit more complete. The limit of the absolute value of an equals 0 if and only if the limit of an equals 0. Okay, this might sound the if and only if might sound confusing to your ears. This is very common mathematics terminology, and you guys are going to be getting exposed to more of this in this chapter. This is kind of a theorem heavy, kind of math language lingo heavy chapter. So I'll explain what this means. In math, we have these theorems, and they're usually stated as something in kind of this form. They're usually stated like if, we'll call it condition, then result. So what do I mean by this? Usually the way theorems are stated is like if some condition holds, then we have some property, like going back up to the squeeze theorem. If we have this, then the limit of Bn is equal to L. Okay. So there's kind of a natural direction here. We have like this statement implies this thing, gives us this thing. So we can kind of think of it as going from here to here. Okay. If and only if means it goes both directions. So what this really means is, okay, this means both if the absolute value of an, if that limit equals 0, so if this, then limit of an equals 0, but it also goes the other way. In when we see the words if and only if, it means it goes both ways. So we have this statement, and we also have this statement. Okay, so we have both of these. All right, so let's just kind of dissect this. Let's start with this, top star here. All right, if the absolute value of an equals 0, then limit of an equals 0. Okay, so let's say again we have some blue sequence. Okay, maybe it can be positive or negative. Boom. Okay, and then we take the absolute value of it, and that turns everything positive, right? So let's do the absolute value in green. Okay, well, if it's positive, it doesn't change, but if it's negative, our absolute value comes up here. Okay. So maybe this is the absolute value, and that absolute value is going to 0, right? Okay. But if this absolute value is going to 0, boom, 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 okay, we know that the original series had to be going to 0 as well, right? Like if this green point is here, then the original point, maybe it was right there, or maybe it was negative just right there. But either way, it's getting close to this line 0. Okay. So if the absolute value is going to 0, the original series is going to 0 as well. And we have the opposite as well. Maybe I start with my original series, and I know that's going to 0. I can see it clearly. Right? Okay, what do I know about the absolute value? Let's do the absolute value in green again. Well, then I know the absolute value is going to be going to 0 as well, right? Okay. So again, we would state that as the limit of absolute value of an equals 0 if and only if the limit of an equals 0. Okay, if that terminology confuses you, just remember that statement is the same as these two statements combined. So a kind of classic example is this alternating sequence. Okay. So let's consider this sequence here. Remember what -1 to the power n means from video 1. That means we're going to have an alternating sign, right? Like in this case, let's see, if I plug 1 into this, I'd have -1 to the power 1. Okay, that's -1. So my first term is going to be positive or negative, right? So my first term is -1 over 1. My second term is +1 over 2. Third term is -1 over 3, and so on. It keeps flipping sign. Okay. What do I know about this sequence? Well, maybe it's confusing if I consider the alternating signs, but take the absolute value of this thing. What's the absolute value of -1 to the power n over n? Well, that absolute value, all the negatives get turned positive, and what I end up with is just 1 over n. What do I know about this sequence? Well, limit of an, let's call this, we'll call this bn. Okay. Well, let's just call it what it is, 1 over n. We know that the limit of this thing is 0, right? And this is the absolute value of -1 to the n over n. All right, so since the absolute value goes to 0, the original series has to go to 0 as well. Okay. Moving on, this theorem is very extremely useful. And I apologize for just throwing a bunch of theorem. A lot of this, I'm trying to give examples for all the theorems I do. Okay. But at the end of this video, since this section's so long, it's got a lot of material in it, it's just going to seem like I'm throwing just a wall of theorems at you. The rest of the sections are a bit better about that. It's less of a chunk of material for each section. So we just got to get through this section. So this theorem, this is a very important one. If the limit of an is equal to L, so we have some sequence and it's going to some limit L. And the function f is continuous at L. Then the limit of f, the function of the sequence, the limit of that function of that sequence, that equals f of L. Okay. So look at this theorem, think about it for a second, pause the video if you need to, and now I will explain. Okay, so what does this mean? Let's say we have a continuous function given by this curve here, and let's call it f. All right. And we have just some number on the x-axis L. Okay. And remember what it means for this function to be continuous at this value L. It means as we move closer and closer along the axis towards L, well, I should do it more like this. As I move closer and closer to this L, right, as my x values get closer to this, my function values get closer and closer to that point. Okay, that's kind of the more rigorous way to think about this, instead of thinking of a continuous function as like one you can draw without lifting your pencil. Another way to think about it, the more rigorous way, is saying, okay, if I move close to L, then my curve has to move close to f of L. All right. Now let's put this in the context of a sequence. Let's say I have a sequence, and let's do it in green. Let's say I have a sequence an of points, okay? And my points are moving closer and closer to L. Then what about f of my sequence, okay? If these points are going close to L, right, then since my function is continuous, I have to be getting close to f of L. So that's all this is saying. But the result is the technique we get from this is very powerful. In that, let's say I have a limit, I have a sequence. I'm trying to consider a sequence. I'm trying to see if this converges to a limit or not. I want to find the limit of this if it exists. And it's kind of all my n's are inside of a continuous function, right? I know sine is a continuous function, and now all my n's, all the changes in my sequence are kind of inside that function. Well, this might be confusing to say the limit of the sine of pi over n, but as long as sine is continuous, we can view this as sine of the limit of pi over n, meaning we can take limits inside continuous functions. Okay. And now forget about the sine for a second. What's the limit of this? What's the limit of pi over n as n goes to infinity? Well, pi is just a constant, and then we're dividing by a larger and larger number, right? So this limit goes to 0. And so I should just have the sine of 0, which is equal to 0. So, and it's not even that many steps, right? It's basically just about switching, or not switching, but, maybe bringing the limit inside the continuous function. Okay, so it's a very powerful technique. This here, if you can understand it, great. This is more a justification for this technique we're using. Okay, so let's do one more example. All right, let's say we wanted to find the limit of this thing, ln, the natural log of 1 plus 1 over n. Okay. First, I ask myself, I try and take the limit inside. Let's try and take the limit inside first. Okay, ln is a continuous function, right? It's not continuous at 0, but it's continuous, for all positive numbers. Okay. All right. So I take the limit inside. Okay. And now this limit's pretty easy, right? The limit of 1 plus 1 over n. I know this part's going to 0, so I have essentially 1 plus 0. So the limit of the stuff inside is just 1. Okay, so I should have this. And then I just go back and maybe I ask myself, okay, is the ln function continuous at this value 1, right? In the terms of our theorem, the 1 is our L. Okay, so we need ln to be continuous at L. 1. And it is, right? ln is continuous at 1. Okay, the graph of the ln looks like this, okay, where this is 1. So yeah, that's continuous at 1. Okay. So the limit of this is, I take the limit inside. This part becomes 1. So I have ln of 1, which is equal to what? It's equal to 0. So the limit of my original sequence, this thing, is equal to 0. And this is kind of a special, it's kind of a special case of this continuous function thing. But if you just want to consider this as its own little idea, that's fine. We're going to see this a lot, or variations of this. What's the limit? Let's say r is some constant number, and then my sequence is I'm taking r to different powers. Okay, so taking r to bigger and bigger powers. Is this thing convergent? Okay. It is under certain circumstances, right? Think of a fraction, right? And let's start with like 1 over 4. Okay, let's say this is my r, and then I do, I square this. What's happening to my fraction? Is it getting bigger or smaller? Well, it's getting smaller. All right, it's getting smaller and smaller and smaller. But it's always, in this case, it's always positive. Okay, if we're starting with a positive number, our fraction is always positive. but it's getting smaller and smaller and smaller. So we kind of expect it to go to 0. But what about, in this case we had a fraction. What if it's not a fraction? What if it's, some whole, let's say some whole number bigger than 1. Let's say r is equal to 6. Then what's happening? Well, r squared would be 36. It's getting bigger. R cubed is, oh God, I don't even know what 36 times 6 is. Let's see. 216. But it seems to be getting bigger and bigger and bigger, right? So in this case, maybe Rn is going to infinity. So it really depends on what our starting R is, right? All right, so the end result is the theorem. I've kind of given some justification for you. If we have this sequence, r to the n is n goes to infinity, well, that's going to be convergent if r is greater than -1 and less than or equal to 1. And it's going to be divergent for all other values. And now let's look at the convergent values of r, okay? This limit, this sequence is going to converge to 0 if r is in between -1 and 1. Why is that? Okay, we kind of saw the beginning of this when we looked at the fraction 1/4. So whenever r is some number in between, strictly between -1 and 1, okay, this number is, you can think of it as a fraction or a decimal. It might not be a nice fraction, but it's less, its absolute value is less than 1, right? So when we take larger powers of it, this number should be shrinking. If r is equal to 1, then if we take large powers of it, it doesn't matter. It's always just going to be 1, right? Like 1 to the power 36, that's still just 1. Okay. So this is where we come up with this rule, okay? If r is anywhere in between -1 and 1, r to the n is going to go to 0. If r is equal to 1, then r to the n is going to go, you could think of it as going to 1 or equal to 1, same thing in this case. Okay. So again, that's a special case, but this r to the n, this, we could kind of think of this as geometric. That term will be more clear in the next section. We're going to see a lot of this. Okay, so get comfortable with r to the power n. Another nice little tool. Okay, we've seen some tools to evaluate limits, and then there's this idea, and I won't classify it as a theorem or technique or anything. It's just kind of this idea. I call it the hierarchy of functions, and that's not unique to me. You can look up hierarchy of functions on Google and find similar stuff. Let's say c is some constant, and let's say it's greater than 1. Then we have this hierarchy of functions here. And what do I mean by a hierarchy of functions? This function grows much slower than this function, which grows much slower than this function, which grows much slower than this function, and so on. Okay. So at this end, we have, at the right side, we have the functions that grow the fastest. Okay. And just so there's no, I know I've done some n's and r's. Okay, these are all n's in this line. And then I have a c here. Okay, c to the n is here, and then n to the power c is here, n to the power 1 over c is there. Okay, everything else is n's. So what does this mean? As n gets big, this function grows a lot faster than this function. Okay, what do I mean by that? Let's think of kind of this slow growing function ln of n. What does the graph of that thing look like? Kind of looks like this, where it seems like it's trying to level off, right? Ln of n, it actually keeps growing for, forever, and it will eventually get to infinity. Well, I guess it'll never actually reach infinity, but it just keeps growing and growing and growing towards infinity forever. Okay, it's unbounded, it just keeps growing. But it's growing really slow, right? On the other hand, if I had something like n squared, which would kind of fall into this category, n to the power c, where c is a constant, what does n squared look like? You know, that would look something like this. Okay. And this is growing really fast, right? I've drawn continuous functions here. Really, we're dealing with sequences, so it'd just be a bunch of points, right? But same idea. You know, this holds for continuous functions as well. All right, so n squared grows a lot faster than ln of n. Okay, great. How does that help us with sequences? Well, let's say I have a fraction and I have a slow growing thing over a fast growing thing. Well, the limit of that sequence, if I have something that grows slow over something that grows fast, that limit is going to be 0. So this limit, ln of n over n to the fourth equals 0. Why? Because this n to the fourth grows so much faster than ln of n. You know, eventually, let's say this is n to the fourth, okay? Eventually, we have, you know, if we go out to 100,000, you know, let's say we go out to x equals 100,000, let's really kind of scale up our graph. Our graph of ln, you know, maybe it looks like this. And then our n to the fourth, maybe it looks like this. Okay, and you know, at 100,000, we'd be way up there. And then for ln of n, we'd still be down here. All right. So that number way up there, wherever it is, maybe it's, you know, it's 100,000 to the power 4. So that's really huge. Okay. And then, you know, ln of 100,000, that's still large, but it's not even equal to 100,000. It's less than 100,000. So it's, you know, this let's see, n to the fourth over n cubed. Okay, if n is 100,000, okay, this fraction, oh no, we had ln of n over n to the fourth, right? So this is less than 100,000. This is 100,000 to the power 4. So this fraction is less than 100,000 to the power 3. So it's getting really small, right? And the farther we go out to the right, the smaller that fraction is going to get, because this n to the fourth just keeps growing faster and faster and faster. This ln of n, it's growing, but it's not growing very fast. So this n to the fourth is just getting farther and farther away from ln of n. Okay. So we have this hierarchy of functions. So the way to think about this is, if I have a fraction, if I divide anything by something to its left, the limit of that is going to go to infinity. If I take one of these and I divide it by something to its right, the limit's going to go to 0. I wouldn't stress about this too much. You know, I wouldn't pour all your effort into hierarchy of functions. It's a nice little trick to have, but you know, most of your stuff is going to be solved in other ways. I would say it's mostly important for n factorial and n to the power n and ln of n, right? Those are kind of the extreme cases. I don't even know if you're going to see any problems like this, n to the power n. That's kind of rare. We will see a lot of n factorial, okay, especially in the later sections when we're talking about series. So I'll go over this more when it becomes more relevant, but remember what n factorial is. N factorial is n times n minus 1 times n minus 2, etc., all the way down to 1, and we stop at 1. Okay. So for example, 4 factorial, that would be 4 times 3 times 2 times 1. Okay. All right, so we talked about this one. This limit is equal to 0. This grows slow, this grows fast. What about n factorial? Okay, well, let's just go up to our, we don't even need to know too much about how n factorial works. We just go up to our hierarchy of functions. I got n factorial here, and I'm dividing by n to the 4th, which it would be in here, okay? So I'm dividing a fast growing thing by a slow growing thing, so that should go to infinity. So, you know, we could say the limit equals infinity, but really what this means is the sequence diverges, right? Okay, if this is infinity, that means the sequence diverges. All right, now let's cover some definitions. Let's say we have a sequence AN. We say it's bounded above if there's some number m, capital M, such that AN is less than or equal to m for all n greater than or equal to 1. Okay. Maybe you think, you know, can a function be bounded? Yeah, of course. Or can a sequence be bounded? Okay. So let's say I have a sequence. Let's do it, the sequence in blue. Okay. And maybe it's growing and shrinking, you know, alternating, but it never goes past, it never goes above that white line. Okay, and let's say that's M. Well, then we say our sequence, this blue sequence, let's call it AN, is bounded above by M. So, you know, we could write AN is less than or equal to M. Now, just because it's bounded above, that doesn't necessarily mean it's bounded below, right? Like our sequence could go down here to, you know, maybe it's shrinking, maybe it's bounded above, maybe it never goes above this M, but it keeps going down forever. So it's still possible for AN to go to negative infinity, right? All right. But on the other hand, we can also talk about being bounded below, right? So AN, we say AN is bounded below if there's some little m such that AN is always greater than or equal to little m. Okay, so what do we mean by bounded below? Okay, I have some sequence. Let's say I'll go ahead and put my little m. Okay, so my little m is here. Okay, I got my blue sequence again. You know, maybe it goes here, boom, boom, boom. And maybe you know, it never goes past this little m. It never goes below it. But again, it might grow forever. Okay, so this one's bounded below, but it might not be bounded above. It might keep growing. Okay. And this little m, you know, that could be, you know, this white line, that could be positive or negative, right? Maybe we're bounded, you know, maybe our axis is here, our little m is here, and our sequence is always above it. You know, it's always greater than this little m. Okay. All right. So we have bounded above, bounded below, and then if we put those together, we get bounded. Just plain old bounded. If AN is bounded above and below, then we call it bounded. Okay. So what would a bounded sequence look like? Well, that would be, you know, there's this kind of window. There's a capital M and a lowercase m, and these might not be the same value, right? This might be positive 100, and this might be like -2. Okay, so there's no necessary symmetry going on there. But if our sequence is bounded, we know it's kind of trapped in between these two for all time. Okay. And I've drawn some, you know, all my points should actually be on this side. Okay. All right. So that's bounded. Now, bound, let's see. I won't confuse you guys too much with what least upper bound and greatest lower bound is, but there's a lot to be said about bounds. I'll put it like that. I think this encapsulates everything you need to know about bounds. Now, let's talk, what does monotonic mean? Okay, we have this word in the textbook, monotonic. Okay, and we're going to combine all these definitions in a second. AN is monotonically increasing if AN is less than or equal to AN plus 1 for all N. Okay, so what does that mean? Again, let's kind of go to this page here, boom. Okay, let's say I have a sequence. It's going to be monotonic increasing if it's always, I won't say always growing, but it's never shrinking. Okay, so maybe, monotonic increasing, it could be constant for a while, but it can never decrease in value. Okay, let's say this is n equals, n equals 1, 2, 3. We can never have our sequence decreasing. Okay, it can only go up. Okay. And then, it goes up, and maybe it's constant for a while again. And then, but then it, maybe it keeps growing and growing and growing. Okay. So I'll say monotonic increasing means never, never decreasing, never shrinking. Okay. But like it can be constant. Okay. So if let's say I have a sequence and it's just constant forever, that would still technically be monotonically increasing. Why? Because it's never decreasing, right? Okay. So that would still be monotonically increasing. On the other hand, a sequence is monotonically decreasing if AN plus 1 is less than or equal to AN, meaning kind of in a similar way, it's never monotonically decreasing sequence. It can never be increasing, right? It might be constant for a while and then descend and then be constant, but it's never going to increase. Okay. And then we say a sequence is monotonic if it's either monotonically increasing or monotonically decreasing. Okay. Oh, I had to go recover my file. I accidentally deleted it. All right. So a sequence is monotonic if it's either monotonic increasing or monotonic decreasing. So for example, if we're told a sequence, we're given a sequence AN and we're told it's monotonic. Okay. How can I think about the sequence AN? I think about it as moving in only one direction. It's either going to be moving just upward like this maybe, or it's going to be moving just downward. And it can be constant for some, a little bit, but it's if it's monotonically decreasing, it's never going to be going upward. So these are monotonic sequences. Okay, why did I give you all these definitions? We have if we combined bounded and monotonic, we get a very powerful theorem. Okay, and I'll show you the way the book states it, and then I'll give you something which I think is better. Okay, so the book states if the sequence AN is bounded and monotonic, then it is convergent. Okay, what does this mean? We have a sequence. It's bounded. So there's some big M and there's some little m that it's trapped in between. Okay, let's do our sequence in blue again. We know the sequence is monotonic, meaning it's only moving in one direction. Okay, so let's say for the sake of argument, it's monotonically increasing. All right, so it's only moving upward. It can never move downward, right? So what does that sequence look like? It doesn't, it doesn't matter what the exact points are. they're all going to behave the same way, right? They're never shrinking, they're always growing, okay? But since it's bounded above, my monotonic sequence can never go past that M, okay? So my sequence has to converge, okay? It has to converge somewhere. It doesn't necessarily have to converge to M, but there's got to be some value. There's got to be some value L that my sequence converges to. Why? My sequence, my blue sequence is growing, right? It's monotonically decreasing, okay? It's growing, but it's bounded above. So it's growing, but it can never go past a certain point. So it has to, you can think of it as it has to stop at a certain point, okay? It's got to stop at some L, okay? And again, that L, maybe, there's not, maybe there's not an L in between. Maybe our sequence grows right up until the point M. Maybe our sequence gets really close to M. Okay. Or maybe our sequence stops before M. Okay, maybe our sequence stops before M. Not that it stops, but maybe it converges to some limit L that's less than M. Okay. So it's really powerful. On the other hand, we have the same idea for a decreasing sequence. If I have, again, I have a sequence that's bounded. Okay. Let's say it's monotonically decreasing, and it's bounded below. Well, it's shrinking, but it can never go past little m, so it has to kind of flatten out somewhere. So there has to be some value L it converges to. Okay. So that's what this theorem is saying. If AN is bounded and monotonic, then it is convergent. So for example, think about 7 plus 76 over n, okay? We don't, if, we could find, this is one of the ones we could solve fairly easily. We could find the limit fairly easily using other techniques we've done. But think about this more kind of in terms of its qualities. This number, right, is shrinking as n gets bigger and bigger and bigger. Okay, this number is constant. So this sequence is monotonically decreasing, okay? But this number is always positive, okay? So this thing is always greater than 7, but it's decreasing. So it's bounded below and it's always decreasing. And it's actually always it's bounded above too, right? This sequence is going to be less than 7 plus 76 over 1. And it's going to be less than that, and it's always going to be greater than 7, right? So we have a sequence that's trapped in between these numbers and it's decreasing. So it's got to be convergent. Okay. Now this is a bit more than we actually need, okay? I'll just state, if you just want to memorize this or just be comfortable with this, that's fine. What we could actually make this a bit better and say, we could split this into two. We could say if AN is, you know what? I'm not even going to say it. It's not worth saying. And it's really, what I have is kind of, what I wanted to say is kind of overkill. And it's really the same thing as this, so it's really not worth saying. Okay. So with that, I will conclude this lecture. This is a section I'll definitely, I'll do a long problem video on this because there's a lot of techniques here. There's a lot of material, so expect a long problem video.